In this video, we'll prove a theorem called Contraction Mapping Principle, also known as Banach's fixed point theorem, which states the following. Let X be a Banach space and S be a non-empty closed subset of X. If this F that maps S to itself is a contraction mapping, then there exists a unique fixed point of F in S. A fixed point is a point in the Banach space that is mapped by this F to itself. We will explain these technical terms such as Banach space, contraction mapping, and fixed point, and some other technical terms that are necessary, and also prove some supporting lemmas and theorems to finally prove this theorem. Okay, let's start. Before going into the details, let me give you one example of contraction mapping and a fixed point. So consider this function f of x equals to hyperbolic tangent of 2x on the closed interval between 0.5 and 1. This function is actually a contraction mapping, and it has a fixed point at this 0.9, 5, 7, and so on. So here's the graph of this function. So this purple line is y equals to hyperbolic tangent of 2x. By the way, this green line is y equals to x. So at the fixed point, this is equal to this. So that's here, and the value of this is 0.957 and so on. A contraction mapping means that if you pick any 2 points on the x-axis, for example like this, and calculate the distance between them, and find the images of these points, and calculate the distance between the images, so this distance, and compare this distance with this distance. A contraction mapping means this original distance is always greater than or equal to this distance between the images. So what the contraction mapping principle says is that if we have such a function or mapping, then we always have somewhere a point that processes this identity map. This is a very simple example in one-dimensional space, but contraction mapping principle is applicable to any dimensional spaces, or any abstract spaces for that sake, as long as it is a Banach space. To explain what a Banach space is, we need the notions of normed space and norms. So first, let's define a norm. Let X be a vector space over the field K. So the field K means something like the set of real numbers or the set of complex numbers where we can do usual arithmetics. And the function, written as this one, from this X vector space X to real numbers is said to be a norm if it satisfies the following three axioms. First, for all elements U of X, the norm of U is greater than or equal to 0. It's non-negative. And in particular, if the norm of U is 0, that means U is 0 and vice versa. And second, for all element of the field K, alpha, and element of X, U, so it's a vector space, so we can define the scalar multiplication between the scalar alpha and the vector U. So the norm of alpha U is equal to the absolute value of alpha times the norm of U. And third, the triangle inequality means for all elements U and V of the vector space X, the norm of their sum is less than or equal to the sum of their norms. So this is a typical triangle inequality. So any function on a vector space that satisfies these three conditions can be said to be a norm. Based on this notion of the norm, we can define the normal space as a set on which a norm is defined. So, the usual vector space, where we can define a norm as the length of a vector, is a normal space. And possibly the simplest example is this. The set of real numbers with its absolute value as a norm is a normed space. Because we can consider the set of real numbers as the one-dimensional vector space, and we can easily see that the absolute value of real numbers satisfies all these axioms. So it is a normal space. Next, let's review the definition of the Cauchy sequence. Let X be a normal space with a norm written as this, and a sequence A1, A2, and so on that continues to infinitely in X is said to be a Cauchy sequence if this is satisfied. So the difference between two different terms in the sequence, as these indices m and n go to infinity, the difference converges to 0. So if this is satisfied, this sequence is said to be a Cauchy sequence. Then we define the completeness of a set. A space, a normed space, in which every Cauchy sequence converges, is said to be complete. Perhaps you have learned in calculus course that every convergent sequence is a Cauchy sequence, but the converse is not always true. To see this, consider this example. Consider the normed space Q with absolute value. Q is, of course, the set of rational numbers. And consider the sequence defined by this. So the first term is 2, and after the second term, we have this. an minus 1 squared plus 2 divided by 2an minus 1. Okay, so after the first term, we can calculate the second term based on this. So put 2 into here and here, then we get the second term. And if we get the second term, we can get the third term and so on. Actually, this sequence is obtained from the Newton's method for solving x squared minus 2 equals to 0. Now you should try to find this. Anyway, this is a Cauchy sequence because we know that it converges to square root of 2. But it's not a convergent sequence within this set because, of course, the limit of this sequence is square root of 2, which is not a rational number. Therefore, this normal space, the set of rational numbers with absolute value as its norm, is not complete. On the other hand, the set of real numbers with the same norm is complete, of course. In fact, one way to obtain the set of real numbers is by completing the set of rational numbers. Now we can define the notion of the Banach space, which is nothing but a complete normal space. Easy. The completeness of a space is important because we want to deal with continuity of mappings. If a space is not complete, we can't deal with continuous mappings in that space. Now let's prove this lemma about absolutely converging series and completeness. Let X be a Banach space, so it's a complete normal space. Then this series converges in X if this series is convergent. So this series is the sum of the norms of the terms of the original series. When a series satisfies this condition, it is said to be absolutely converging. Because in the case when this X is the set of real numbers, this norm corresponds to the absolute value. Therefore, absolutely converging. So because it's converging. So let's move on to the proof. Let us define Sn as the partial sum of the series. and pick some natural numbers m and n with m greater than n. Then take the difference between Sm and Sn and take the norm of the difference, which becomes this. So this is the sum of the terms xk, where k runs from n plus 1 to m. And the norm of the sum is less than or equal to the sum of norms according to the triangle inequality. And as n and m go to infinity, this whole sum converges to 0 because we're assuming this. If this doesn't converge to 0, then this should diverge, but that's not the case by assumption. Therefore, this sequence Sn is a Cauchy sequence, but we are assuming the space X is a Banach space, which is complete. Therefore, this Sn converges. That means this series converges. Then we are done. Now, let's define the fixed point more formally. Let F be a mapping with its domain and codomain being subsets of X, where X is some space. A point X, lowercase x, in the space X is said to be a fixed point of F if X is equal to f of X. So if X is a fixed point, then it is mapped to itself by the mapping F. Next, let's define contraction mapping. Let X be a normed space, a mapping F from its domain to codomain, both of which are subsets of X. It's said to be a contraction mapping, or simply contraction, if there exists a constant R, which is between 0 and 1, including 0, excluding 1, such that for any 2 points in the domain, this difference, the difference between the images of the 2 points, is less than or equal to R times the difference between the 2 points. So this is basically what I have explained in the example at the beginning of this video. So the distance between the original points in the domain is greater than or equal to the distance between the images of the 2 points. So that is expressed by this constant R, which is less than 1. Right before proving the contraction mapping principle, we need this simple lemma that says a contraction is continuous. To prove that, let's say this epsilon is any positive number. If the distance between x and x prime, of course these are assumed to be elements of the Banach space X, is less than epsilon, then the difference between their images is less than or equal to R times the distance between the 2 points x and x prime, because we're assuming f is a contraction, right? But we're assuming this distance is less than epsilon, so this is less than R times epsilon, but R is less than 1 and greater than or equal to 0. Therefore, this R epsilon is less than epsilon. So for any epsilon, this holds, as long as the distance between x and x prime is less than epsilon. Therefore, the contraction F is continuous. We can finally prove the contraction mapping principle. Let X be a Banach space and S be a non-empty closed subset of X. If a mapping F from S to itself is a contraction mapping, then there exists a unique fixed point of F in S. To prove this, we split into 2 parts. First, we prove the uniqueness of the fixed point, and then we prove the existence of the fixed point. So let's start. First, uniqueness. The usual way to prove uniqueness is to assume there are 2 such things, right? For example, x and x prime, suppose they are the fixed points of F. Then we eventually show that they are actually equal, okay? This is a basic technique to prove uniqueness. Okay, so since we are assuming both x and x prime are fixed points, we have x equal to f of x and x prime equal to f of x prime. So if we take the difference between these two, on the one hand, we have x minus x prime, its norm is equal to the norm of f of x minus f of x prime. Now, since we're assuming this f is a contraction mapping, then there is some r between 0 and 1 such that this difference between f of x and f of x prime is less than or equal to r times the difference between x and x prime. So this was the definition of contraction, right? So this should hold. However, this is equal to this. So we can replace this with this. Hence, we have the difference between x and x prime is less than or equal to r times itself. So from this inequality, we have 1 minus r times the difference between x and x prime is less than 0, right? So if we move the right-hand side to the left-hand side, we have this. So we have this. On the other hand, r is between 0 and 1, so this 1 minus r is positive. And the norm is always, of course, positive. So this whole thing is positive. So 1 minus r times this norm is between 0 and 0. But 1 minus r is strictly greater than 0. Therefore, this part is positive. So if we divide everything by this term, we have this norm between 0 and 0. So that means this is just 0, which means, according to the axiom of the norm, this implies x is equal to x prime. Therefore, we have proved the uniqueness of the fixed point. Now let's prove the existence of the fixed point. So far, we have only proved the uniqueness, right? If fixed point exists, then it is unique. But what if it doesn't exist? So we need to prove the existence so that this theorem makes sense. First, let's pick any point x0 from the set S and define a sequence x1, x2, and so on by this equation. So this is a recurrence equation. So each xn is defined by f of xn minus 1. And since this mapping f maps from S to itself, this xn is always within the set S. So this holds for all natural number n. Next, consider this difference between xn plus 1 and xn and take the norm of it. So this is equal to this because we define each xn by this equation. So this is okay. And since f is a contraction mapping, then this whole thing is less than or equal to some constant r times the difference between xn and xn minus 1. So this xn is the argument of this f, and this x minus 1 is the argument of this. And we can continue this again and again and again and finally get this whole thing is less than or equal to r to the power of n times the difference between x1 and x0. Now, on the other hand, each xn plus 1 can be expressed as a sum like this. So xn plus 1 is here, minus xn, adding xn again, so they will actually cancel, and this will cancel with another term, and so on and so on, and everything else cancels. So xn plus 1 is expressed as a sum like this, which we summarize as this. Okay, so this xi plus 1 minus xi I runs from 0 to n. So this type plus this and so on, and add the final term. Next, based on this, consider this series, okay, one constant plus a series. So from this inequality, we have this series is less than or equal to this series. So each of these norms is replaced with this norm times this constant, r to the power of n. And this is a constant, and this is just a geometric series. So its sum is 1 over 1 minus r. And of course, this is a constant, less than infinity. So this is absolutely, this series, so if n goes to infinity, this series is absolutely converging. And we have proved in lemma 1 that absolutely converging series is converging or convergent. So this series is convergent. That means if we take the limit n going to infinity, then this xn plus 1 will converge to some value. I mean some value in the set S. Since any contraction is continuous, as we have proved in lemma 2, this limit exists. So f of xn, if n goes to infinity, then this sequence converges to this value, f of x star. So x star is this one, is the limit of xn. And from the first equation, this one, the defining equation of the sequence, then we have xn equals to f of xn minus 1. So this converges to x star, and this converges to f x star, and they are equal. Therefore, a fixed point exists, and we are done. Okay, that's all for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.